Guys, we're starting part 2 review of Unit 5. I'm going to go ahead and start with number 9 and probably do all of A. A few things we need to know for number 9, 10, 11 are average rate of change formulas. Okay, so quick review. You guys should be seeing this on Plato, but in case you're not, average rate of change is this formula of f of b minus f of a all over b minus a. Okay, so if you're seeing this for the first time, maybe this quick run through, you might need a little bit more than that and it might not be helpful, but as a review, we're doing this average rate of change formula and we're finding it over a given interval. All right, and we normally reference the a as, that's an accident, let me move that down here. The a is the start of our interval and b is the end. Okay, so if I'm looking at our interval here, it's talking about the change over 1 to 3. All right, where a is going to be the 1 and b would be 3. And if I was like doing that here, all of these numbers would change. If you're looking on a graph, even though in this case the average rate of change will be constant over this interval since it's linear, if it was something different, I would only be looking at the interval from 1 to 3. Actually, I'm a little bit off. That's this is 4 there. We actually want 1, 2, 3 right here. And even though for this particular function, since this is a linear function, looking at that red line, the average rate of change will be constant throughout. We can find the average rate of change for just this region, which is 1 to 3. Now, when we get down to a problem like number 11, it's not abundantly clear, but this is an exponential function, so this is not a straight line anymore, and your average rate of change will be different from one interval to a different interval, and then over your function overall. So taking it back to where we were starting up here, B and A, those reference your specific x values, and then think of A and B as your x values. This is the leftmost x value, and this is the rightmost x value. B, think of B being bigger, will always be the bigger x value. So especially if you're working with some negative values, you can use that as a point of reference. And the f of B and the f of A, these are outputs at those specific x values. All right, and we'll kind of get into some examples. Excuse me. So hopefully it'll be a little bit more clear when we go through some of them. Now, using this average rate of change formula, sometimes you are presented your information in different ways. For this very first example that we'll go to in a moment, they give you an equation, or a function that you'll actually plug in your values. The second example we'll do, they give you a chart. It's a little bit easier because I can directly read the values. Like as we had mentioned, the a and the b are x values. So if I wanted to know the a value of the specific function, it would be like plugging in 1 here, and I get 6. So we'll get to that in a moment and kind of repeat that. But let's get into this very first one. This one's probably the more challenging of the 3, just because we've got to do a little bit extra work. Now, I will write the formula here. F of B minus f of A all over B minus A. And then be careful with the order because the order does matter. We don't want to switch and do a BA order and then an AB on the bottom. Now, looking over here, remember our B value will always be the biggest value or the rightmost x value. So in this case, our B value is 3. And our smaller value or our leftmost value is 1. So let's plug that in. F of 3 minus f of 1 all over 3 minus 1. Now the part that's the easiest to calculate here is the denominator, because I can do 3 minus 1 fairly easily in my head. The part that I have to do a little bit of calculations is the f of 3 and the f of 1. Alright, so remember, if you have f of 3, that means you're plugging 3 into your function. So instead of saying, if we're referencing this f of x function, instead of saying f of x is equal to negative 4/3 times 2 to the x power, if we were to reference, I guess we want f of 3. f of 3, recall that the difference between this and this are these right here. So everywhere on the right side, the only thing that would change are these x's. So f of 3, and I kind of got a lot of stuff to look at going on there. When I write f of 3 or solve for f of 3, I'm going to be getting negative 4/3 times 2, and I will change that x to a 3. The only thing that changes is the x. Okay? And then I will solve that out. So I'm going to rewrite that kind of built into my fraction already. That's the one in purple. Let's maybe use a different color. So this is all equal to f of 3 would be negative 4/3 times 2. Plug in the 3. Then I need to subtract f of 1. And then you'll notice that we are going to get a double negative, so that will turn into a positive or a plus in a moment. 2 to the 1 power. And then this is all over 3 minus 1, and I'm going to go ahead and do that simple math right there. Now, if you'd like, it might make your problem a little bit easier if you notice some things that we can factor out. Something I might consider factoring out are the negative 4/3, since there's a negative 4/3 in both. Maybe you change the sign first and then do the factoring. So I'm going to go ahead and change these. So this is going to be a plus. But back to the factoring. Maybe I would want to factor out a negative 4/3 or just the 4/3, since they both have it. And then I also noticed that they both have 2's in them. Like 2 cubed is going to be 2 times 2 times 2. So I can factor this out and be left with a 2 squared. So I won't do that here because we haven't gone in that much into factoring. I don't want to. I just want to do it maybe like a little bit simpler beforehand. But if you're on that level, if you want to ask me a little bit more about the factoring, we can definitely do that. But let's just start evaluating negative 4/3 times 2 cubed. That is going to be times 8. And then this is a plus 4/3 times 2. This is all over 2. Let's see. This is going to be, I have to multiply those fractions to the part into the parentheses for both of them. Remember, if it helps, when we're multiplying fractions, we're multiplying straight across. So if it helps, you can write 2 and 8 all over 1, and we'll multiply denominators and numerators each to each other. So on the top, I would get negative 32 over 3 plus 8 over 3, and then I still have that 2 in the bottom. I'm going to, let me minimize some of this so we fit in the box again. Zoom into here. Let me combine what I've got going on up in the numerator. So negative 32 over 3 plus 8 over 3, since I have similar, common denominators, I can simplify that and get negative 24 over 3 all over 2. And negative 24 over 3 simplifies nicely, which gives me negative 8 all over 2, and then this is equal to negative 4. Okay, so my average rate of change for this function over the interval of 1 to 3 is negative 4. Okay, Now let's do that a simpler example here. Let's find the average rate of change for g over that same interval of 1 to 3. Now I'm not going to go through the whole f of b minus f of a all over b minus a, writing that down. But if you like, I will write g of 3 minus g of 1 all over 3 minus 1. Okay, now this chart has already evaluated the function. They don't tell me what the equation part of this function is, but they tell me what it's evaluated at. So looking at, if I was to plug in 3 to this function of g, I would get 10. All right, so in place of g of 3, I'm going to put 10. And then I will subtract whatever g of 1 would be evaluated at, which is 6. And this is going to be all over 2. Let's just simplify a bit. 10 minus 6 is 4 over 2. And then 4 over 2 is equal to 2. So your average rate of change for that interval, 1 to 3, for g, is 2. Now, looking at our third example over here, this graph, it is actually a little bit simpler because I noticed that it is a linear function. It's a straight line. And one of the things we've talked about is if we have a linear function, the rate of change will actually be constant. And that is given to us by our slope. So if you can figure out your slope, and I can figure that out, if you pick out one point, say starting with the y-intercept where we normally start, and go up 3 over 1, I can tell that my slope is 3. So my average rate of change will be 3 throughout the entire graph, including my interval between 1 and 3. All right. However, we can't always bank on having a line for a graph that we're going to read off. And in particular, when we get to number 11, we're going to have to figure out the average rate of change by pulling the points off. So I want to give you a little bit of practice of seeing what that would look like. So if I'm looking for, and I didn't write it here, but let's call this h. Let's call this whole function h, or h of x. I can't really, I'm having some trouble getting that x. All right, so I'm still looking for the same interval, and I'll write up here. Hopefully the graphs and the grid doesn't get confusing. So similar, I have my start up the same. Now h of 3, that means I figure out at the x value of 3, which is 1, 2, 3, where does it hit my graph? So I'm going to be looking at, here's 3, I'm going up, and I hit here, and at this particular value. So let me move this so I can see a little bit clearer. It is hitting right there, which looks like 7. So h of 3 is 7. Now let me do the same thing for h of 1. My x value of 1 is right here. I'm going to go up till I hit my graph, which is pretty quickly right there. This value is 1. So this is going to be 7 minus 1 over 3 minus 1, which I'll go ahead and simplify. This is 6 over 2, or 3, which matches up with our slope, which we had said it would be 3. Okay. Let's go down to number 10.